feel free to post in the chat, which you guys are discovering right now. You can also turn on your microphone if you wanted to like just talk to me at some point as well, okay? All right. Okay. So I'll talk a bit about what we're going to be doing today. One second. All right, sorry, just had to take care of something. Okay. So over the next 3 days, we're just going to be going over some of the like first couple of concepts that you'll encounter in your calculus courses. For you who maybe have taken calculus already, maybe you took AP calculus. Uh, all of this would kind of be like for you, but you kind of have in mind like people who haven't taken calculus before. So I'll be kind of introducing the various concepts to them as if they had never seen it before, okay? And I'll be working through some examples, of course, and I'll also, at some points, have you guys like work on a problem that I'll assign. And so give you guys a couple of minutes to work on a problem, and then we'll kind of discuss it as well afterwards. Okay. So again, have questions, post in the chat or speak up to your microphone. And yeah, I was a little bit afraid of that. Okay. My connection is a little bit spotty right now, so yeah, okay. I'm not sure what I can do about that. Let's see here. Let me try and see if I can fix this. Yeah, okay, so I don't know if that fixed it, but I just kind of tried refreshing my browser because I didn't know what else to do. It sounds better now. I'm going to try sharing my application again. It might be that when I share my application, it'll get bad again, but we'll see. Yeah, okay. My connection seems to get a little bit worse as I'm sharing something. Hopefully that won't be too much of a hindrance. So we'll try to make do for now. Okay. All right, so I'm just gonna go ahead and get started. So before I start doing any sort of problems, I just want to give a sort of overview on what exactly is calculus, okay? So this is like a sort of slideshow that I created in summer 2020. So that's why it says summer 2020 on the first slide here. And so I'm just gonna go through like a portion of the slideshow just to kind of go over, what is calculus, okay? Some of you may have seen this before already. If you were maybe browsing our YouTube channel, then you might have seen a video on this. Okay, so what is calculus? So in calculus, there's kind of like three objects of study that you're going to learn about. So in the order that you'll see them, you'll learn about limits, derivatives, and integrals. Um, so whether you're going to be taking 2413 or 2417, you'll see all three of these by the end of the first semester. Um, and then 2414 and 19, we'll just kind of go more in depth into some of these. Okay. And so to get a sense for what these three objects are, how do we use them in calculus, I wanted us to consider the following problem. So I've got a picture here, and let's say we want to try to find the area of this figure. So this figure, it's a complicated figure, of course, so we don't have a simple formula like base times height or like pi r squared or anything like that to calculate this area. So if we're thinking about how would we even try to approach this problem, one thing that we could do is we could start by just trying to get an approximation of what this area is. So in order to approximate it, what we're going to do is the following. We're going to start by just dividing the region into smaller pieces. So here's an example where I've divided the region into 4 smaller pieces. Okay. So what we're going to do is we're going to approximate the area of each of these pieces. And then we're going to add everything up, and that should give us an approximation for the total area. So here I'm focusing just on like the first piece right now. So what we're going to do is we're going to approximate each of those pieces as a trapezoid, okay? So all I'm doing is I'm just kind of like ignoring the top curvy part and just replacing it with a straight line segment. Let me see what's going on. Let's see here. Oh, that's odd. Okay, I didn't know that it would do that. Okay. Yeah, 1 second. I can go ahead and fix that. So on my end, I have it in like a sort of presentation mode, but I'm noticing that that doesn't actually get shared in e-learning. That's kind of interesting. So give me a second. I'll fix that. Okay. So yeah, let me try to just share my screen instead. Okay. This. Okay. Yeah. So I'll just go back real quick. So the problem was to try to find the area of this region. Okay. And the way we're going to do that is we're going to start by approximating it. So what we are doing is we're going to divide the region into smaller pieces. And then what I'm doing is for each piece, I'm going to approximate each piece as if it were a trapezoid. So all I'm doing is looking at the top and I'm just ignoring that curvy portion of the graph. And I'm just going to pretend that it was like a straight line segment instead. So we have a formula for the area of a trapezoid. It's the average of the two bases times the height. So we could use this formula to get the area of the trapezoid, and that'll give us an approximation of the area of the original piece that we were looking at. And so already I've done something that's kind of profound, actually. So this idea of like replacing the curvy portion at the top with a straight line segment, this idea of a linear approximation, that's kind of the whole idea behind derivatives, which is one of the three objects of study that I mentioned at the start. So that's kind of where derivatives come into play, is this idea of linear approximation. Okay. So we're going to do that for all four pieces. Okay, so here, replace each of the pieces with a trapezoid. Okay. Add up the areas of the trapezoids, and that will give us an approximation of the area of the shaded figure. Now, of course, it's just an approximation, so as you can see, there's like a little bit of error. So here, this area was not counted. Whereas over here, you can see that we counted a little bit too much area with the trapezoids that we were using, okay? But still, it will give us a decent approximation, and we could repeat this process using more pieces. So here's a picture where I'm using 10 pieces now. And then for each piece, I again approximate each piece as a trapezoid. And when you look at this, the approximation seems to be a lot better. So you don't really notice much error anymore, although of course there is still some error. So there's this idea that the more and more pieces we use to approximate the area, the better our approximation will get. So we have an idea that maybe the actual area of this figure would be the number that we will get if we could continue this process indefinitely. So like repeating to infinity. And then this is where the notion of a limit will come into play. So limits in calculus, limits are used to like calculate what lies at the end of an infinite process, okay? Let me just see what the comments are. Okay, cool. All right, and then this whole process of like taking a problem and breaking it down into smaller pieces and then kind of like adding all those pieces up to get a solution to the original problem. That's where integrals come into play, okay? So just to kind of summarize what we've talked about just now. So in calculus, you'll be learning about limits and derivatives and integrals. So limits, what they do is they help us to find what lies at the end of an infinite process. Derivatives, what they're used for is they're used to approximate something complicated, i.e. nonlinear, with something simple, i.e. something linear instead. And the integrals are what allow us to sort of like combine or add up all the tiny pieces of our problem into like a coherent whole, it's like a solution to the original problem, okay? Yeah, okay. And so throughout the next 3 days for these workshops, we're just going to be diving into limits. So we'll be talking about like what are limits, different types of limits, how to work with them, and so forth. Maybe towards the very end of the workshop, we can maybe get into derivatives a little bit. But with the time that we have, we'll probably mostly be focused on just limits, okay? So then to try to actually answer the question of what is calculus, this is kind of the answer that I came up with years ago. So I said calculus is the art of taking a complicated problem and then solving it with some sort of a infinite approximation schema using limits, derivatives, and or integrals, okay? Okay, and then for the rest of the slide, I'll come back to it later, but I'll pause here for now, okay? So what I'm going to do next is I'm now going to move on to like the actual meat of the workshop, if you will. So we're going to start like actually doing some math, okay? Yeah, I can definitely share the slides with everyone. So maybe when we upload the recording to our YouTube channel, I'll include a link to the slides in the video description, so that way you guys will have access to it. Okay. Okay, so to start with the workshop, so I wanted to go over limits, and specifically what we're talking about, limits of functions. And before I start like actually doing any examples, I wanted to just sort of give a sort of graphical illustration of what limits of functions are. So I'll kind of introduce you guys to some of the notation that we use for limits and some of the different types of limits as well. So I have here the graph of a function, and as you can see, it's a pretty complicated graph. There's a lot going on. So I'm just going to look at certain parts of the graph and talking about limits and what they are in the process. Yep. So let's start by looking at this first point here. Maybe I'll change color. All right, so I'll look at this point first. It didn't quite. Oh, that's interesting. I see. I guess when I shifted my picture earlier, it didn't shift the points. It only shifted the graph. That's kind of inconvenient, but that's okay. Okay, so let's look at this first point here. So this first point, it's a little bit off, but pretend that the x-coordinate was -5 and the y-coordinate was -4. That was my intention. Okay. So when you look at the graph of this function, so of course you can kind of see as x gets closer and closer to -5 here, if you kind of follow the graph, the function is going to be getting closer and closer to this point, right? So the way that we want to describe that using limits is we want to say that the limit, let's say as x is approaching -5 of this function that we're looking at, we want to say this limit is, or sorry, this function is approaching the value of -4 as x is approaching -5, okay? So that's just as you move closer to -5 along the x-axis, you can see that the function will be moving closer to this point at -4, okay? Now, in contrast, if we look at what's going on over here, where x is equal to -2, okay? So when x is -2, there's kind of a break in the graph, as you can see. And here again, when I was moving the graph around, it kind of moved only, I think, the axes, but not the points or something like that. So this point here should actually have an x-coordinate of 2 and a y-coordinate of 1. So just pretend that is the case. Okay. And here it's a little bit more complicated. So as x is approaching -2, this time if you follow the graph, depending on what side you're approaching -2 from, the function appears to be approaching like 2 different values, okay? So to reflect that, there's also a notion of like a one-sided limit. So what we might say here for this function is if we were to look at the limit, say as x is approaching -2, but from the left, yeah, what's happening to our function? So if we approach -2, but from the left, and then we look at what the graph is doing, we see that the graph is approaching this point, which is at -1. So we would say that as x approaches -2 from the left, this function approaches the value of -1, okay? So notice that here, like I put like a minus superscript on the -2, and that indicates that we're approaching -2 from the left. Uh, Now, if we want to talk about what's happening if we approach -2 from the right, we would notate that by using a plus sign as a superscript. So this is saying x is approaching -2 from the right. And so as x gets closer to -2 and from the right, we follow the graph and we see that the graph is approaching this point with a value of 1. So in that case, we'd say the limit is going to be equal to 1 instead, okay? Yeah, yep, okay. And so something similar is happening at x equals 2. So that's over here. So if we approach 2 from the left, we look at what's happening with the graph. Okay. So as we approach 2 from the left, we see that our function is approaching this point at a y value of 3. So we would say the function approaches a value of 3 as x is approaching 2 from the left. Whereas in contrast, if we have x approaching 2 but from the right, okay. So in this picture, as x gets closer to 2 but from the right, we follow what the graph is doing. Here the function is approaching this y value of -1. Okay. Now as for what this point here represents, though, so the way that you would read that is this is saying the function, the function evaluated at x equals 2 is actually equal to 1. So that's what this point here is representing, okay? So here you can kind of see that the actual value of the function doesn't matter as much when you're talking about the limit. So the limit is really looking at what is the function approaching. So in these cases, approaching like 3 from the left or approaching -1 from the right. But the actual value of the function was equal to 1 instead. It's kind of worth noting that limit only talks about what the function approaches and not necessarily what the function is actually equal to. At x equals 4, we have something interesting going on as well. So at x equals 4, we have these, we have this vertical asymptote at x equals 4. Yes, that's right, yeah. So the open circles are actually holes, so wherever there is an open circle, that means the function is not like actually defined at that point or with that value, okay? Okay. So at x equals 4, we have this vertical asymptote, and if we try to think about limits again, So the behavior of the function is a little bit different as you approach 4 from the left and as you approach 4 from the right. So again, when that's the case, it's useful to talk about one-sided limits. So what would we say that our function is approaching as x approaches as x approaches 4 from the left? So following the graph, as x gets closer to 4, but from the left, the function this time, it just like keeps going further and further down. So what we would say is that this limit is equal to negative infinity. This function just keeps going further and further down, and we would sort of say it approaches negative infinity. So here we see that limits can be infinite. And similarly, if we have x approaching 4, but from the right this time, so imagine x approaching 4 from the right. Look at what the graph does. The graph this time just kind of shoots all the way up. And we would say that the function is approaching positive infinity in that case. Okay? Okay. Look at a couple more things going on in the graph. So at x equals 5, again, we have something kind of unusual going on because you've got that hole in the graph at x equals 5. But in this case, if we want to talk about the limit, so for this one, regardless of whether you approach 5 from the left or whether you approach 5 from the right, looking at the graph from both sides, the function is going to be approaching the y value of 4. So even though there's a hole in the graph, meaning that the function is not actually defined when x equals 5, we still see that the function is approaching the value of 4. And so therefore, we would say the limit as x approaches 5 of this function equals 4. Okay. And I also want to address the horizontal asymptotes that are in the graph as well. But before that, actually, let me go back to one of the two-sided limits that we looked at. So let's look at, or one of the one-sided limits. So let's look at this example here where we had x approaching 2 from the left and x approaching 2 from the right. So approaching 2 from the left, the limit was 3, but approaching 2 from the right, the limit was -1. If we were to ask, what is the limit as x approaches 2, like just overall, without specifying from the left or from the right? Well, in this case, the function is not really approaching a single value when x is approaching 2. So whenever you have a situation like this where your function doesn't approach a single value, what you want to say is that the limit does not exist. Okay, so that is a possibility with limits. So whenever the left-sided limit is not equal to the right-sided limit, then the actual two-sided limit you would actually say does not exist. Okay. And then the last thing I did want to take a look at is the two horizontal asymptotes. So we had one horizontal asymptote way over here. And I guess I forgot to label it, but I think this is supposed to be at a y value of -6. Okay. So how would we characterize what's going on with the horizontal asymptotes? In this case, we would say that the function is approaching -6 as x is moving further and further to the left. And so to talk about like x moving further and further to the left, we would say that x was approaching negative infinity. So as x approaches negative infinity, we see that the function approaches this value of -6. And then likewise, when you look at this horizontal asymptote that we had over here, we have a situation where as x is moving further to the right, and to sort of indicate that, we would say as x is approaching positive infinity, our function is approaching this y value of 2. Okay, so we've kind of seen just some examples of limits of functions. So there's a couple of different like types of limits. We have these sort of standard two-sided limits, like this one over here. Jeez. Okay. Then we had examples of one-sided limits where you're only focused on x approaching from either the right or the left. So we had quite a few of those. So these were one-sided limits, for instance. Okay. For vertical asymptotes, what's special about those is that your limits are going to be infinite. So you have infinite limits as a possibility. And then for the horizontal asymptotes where x was approaching infinity or negative infinity, these are usually referred to as like limits at infinity. So it's sort of like what's happening as x goes to infinity. So what's happening at infinity, okay? So these are just like different types of limits that you guys are going to be talking about in your calculus class. And we'll try to touch on each of these limits and go through some problems and examples with them over the next 3 days, okay? Yeah, that's correct, yeah. So when the one-sided limits don't match, that makes the two-sided limit not exist, okay? All right. So this kind of gives you a sense of like what limits look like and introduces you to the notation that we use for limits. So I'm going to spend next portion of today just like looking at some examples of evaluating limits, okay? So I'm just going to start with like some really, really simple examples, and then I'll sort of work towards some more complicated situations. All right. So I'll start with something really simple first. So let's do something like the limit as x approaches 3 of x squared. So I haven't really given you guys a formal definition of a limit yet. Just kind of thinking intuitively for now. If x is getting closer and closer to 3, what value would x squared be getting closer and closer to? What would you guys say? Yeah. So I would think your answer was 3 squared, which would be equal to 9, right? So yeah, to evaluate a limit statement as simple as this one, as x approaches 3, what is x squared approaching? Yeah, all you have to do is plug in 3 for x. So we will say the limit is equal to 9, okay? Let's just look at like a few more examples of this sort. So let's do something that looks more complicated. So let's say we'll do a limit as x is approaching maybe pi over 2. And let's do something like sine of x times 3 minus 4x, maybe even squared. And then let's divide that by, let's do cosine of 2x plus 4x minus 1. Okay, so this statement looks a lot more complicated now, okay? But if we try to use the same logic as we did in the first example, as x is approaching pi over 2, what is all of this going to be approaching? Well, let's just plug in pi over 2 for x, the same way that we did in the previous example, how we just plugged in 3 for x to get the answer. So if we plug in pi over 2 for x, so the idea is if x is close to pi over 2, the sine of x should be close to sine of pi over 2, right? Likewise, if x is approaching pi over 2, then we would expect x squared to approach pi over 2 squared, and so on and so forth. So if we just kind of plug in pi over 2 for all the x's, okay, and then if we just kind of try to simplify all of this, in theory, that would give us the answer for what is the limit. So hopefully you guys are pretty familiar with your trig functions. So if you are familiar with the trig, then you'll know that sine of pi over 2 is equal to 1. So we have 3 times 1. For pi over 2 squared, with fractions, when you square them, you just square the numerator and the denominator. So that's going to be pi squared over 2 squared, which is 4. In the denominator, 2 times pi over 2 is just pi. So then if we think about what is cosine of pi, hopefully you guys will know or be able to figure out that cosine of pi is equal to -1. If we multiply 4 times pi over 2, I can cancel out the 2's. So 2 goes into 4 2 times. So that's going to leave us with 2 pi. And then we have minus another 1. So altogether, we have 3 minus pi squared, because here the 4's would cancel. And then that's all over, I guess we can combine the -1's and get 2 pi minus 2. And then that would be the value of the limit, okay? So that doesn't seem too bad. So to evaluate a limit, you can kind of see basically, at least from these two examples, all we need to do is plug in the value that x is approaching, right? So that's what we're kind of observing right now in these two examples. So it's not always going to be that simple. But for now, I just kind of make the observation that to evaluate these limits, you basically just need to plug in what x is approaching. Okay. So the more complicated situations are going to be the ones where you can't just plug in your x value and get an answer right away. Okay. So I want to take a look at those kinds of situations next. So here I've got another example of a limit right now. So as x approaches 3, what is this function going to be approaching? So let's try just plugging in 3 for x, and let's see what happens, okay? So if we plug in 3 for x, you're going to get 3 squared is 9, minus 4 times 3 is 12, plus 3. And then down at the bottom, 3 cubed is 27, and then 9 times 3 is another 27. And okay, here we get something that's kind of nonsensical. So we get 0 over 0, okay? And so I said this is nonsensical. Do you guys know why this 0 over 0 is not an actual answer? What's wrong with the expression 0 over 0? Yeah, so 0 over 0 is not defined. You can't divide by 0. You could use L'Hopital's rule, although we're not going to be talking about L'Hopital's rule in this workshop, I don't think, because it involves derivatives, and I don't think we'll be able to get far enough to talk about L'Hopital's rule. Okay, so I wanted to talk about what's going on when you get 0 over 0 in a limit, okay? So 0 over 0 is an example of what we call an indeterminate form. So let me try to explain what we mean by that, okay? So what's happening in this problem is that the numerator is approaching the value of 0 as x is approaching 3. So we have the numerator is approaching 0. And likewise, the denominator is also approaching 0 as well. So when you have something really close to 0, and then you divide it by something really close to 0, if we think about like what's going to happen when you do that, okay. So like you take something close to 0 and you divide it by something close to 0, the answer that you get will just kind of depend on exactly like how close the numerator and the denominator is to 0 relative to the other. Or if you will, kind of depend on like the relative sizes to each other. So if we maybe consider some specific examples just to try to think about like what's going on here. So let's take a number that we might consider to be close to 0, like maybe 1 over 10,000. Do we sort of agree that's a number that's pretty close to 0? Yeah, okay, that's pretty close to 0. And then let's say we want to divide it by another number that's also something that we would consider really close to 0. Okay, so what would this ratio equal? Well, let's just simplify, right? So remember that when you're dividing by a fraction, you want to flip and multiply by the reciprocal. So instead of dividing by 1 over 1 million, we will multiply by the reciprocal, so 1 million over 1. And then to simplify this, we could essentially cancel out 4 zeros. It's a little bit informal, but it works that way. So we get, looks like the answer is 100 over 1, which is just 100, which is maybe a decently big number, right? But, if I were to just reverse this and say if I do like a 1 over 1 million and divide by 1 over 10,000, if you, just kind of work it out, basically it's just going to be 1 over 100 this time because we just did the reciprocal. So instead of 100, it's now 1 over 100. So what I'm kind of trying to illustrate with this example is if you have something that's close to 0 and you divide it by something close to 0, the answer could really be anything. It could be something that's pretty close to 0, like 1 over 100, or it could be something that's pretty far away from 0, like 100. You just can't really tell what the answer is going to be. So whenever you have this 0 over 0 situation with limits, you can't determine what the answer is from that alone, and that's why we call it an indeterminate form. Okay. So whenever you get 0 over 0 as like the value of a limit, that means that you're going to need to do some extra work to try to resolve that to get like the actual answer, okay? And we'll go over some techniques for how to handle the 0 over 0 situation, okay? But let me just kind of write that down. So, and the key is if you ever get 0 over 0, that means that you have to do more work. So the problem is more complicated. Okay. So let's look at this example again, and let's think about what could we do in order to figure out the actual answer. So whenever you have a polynomial over another polynomial and you're getting 0 over 0, the strategy for dealing with this situation is to try and factor your two polynomials. So the numerator and the denominator, if we want to try to factor them, let's start with the numerator. So x squared minus 4x plus 3, who can tell me how that would factor? It's, yeah, x squared minus 4x plus 3. Yeah, so that would factor as x minus 1 times x minus 3. That's good. Now in the denominator, if you want to factor that, yeah, So what you guys will want to do is factor out an x first. So x cubed minus 9x, you can factor an x out from the two terms. So that'll leave us with x times x squared minus 9, okay? And then x squared minus 9 can be factored even further. So if you were to factor x squared minus 9, yeah, so it should factor as x minus 3 times x plus 3, okay? Yeah, so this is the difference of squares formula, okay? Now, once we fully factor it out, what we see is that we have an x minus 3 in the numerator and the denominator. So we can actually cancel these factors of x minus 3. And then once we make the cancellation, what we can do is we can try plugging 3 into the problem again. So this time, if we try to plug in 3 for x, we're going to get 3 minus 1 is 2 in the numerator. And then we plug in 3 for x, so we've got 3 times 3 plus 3, so 3 times 6. And then I guess 2 will go into 6 3 times. So you've got 1 over 3 times 3. So now we will get an answer of 1 over 9, okay? All right, so let me kind of summarize and just highlight a couple of things. So whenever you have a limit like this where you've got a polynomial over another polynomial, and let's say that you have that 0 over 0 indeterminate form when you first try to plug in per x, your strategy for dealing with this is to factor. So maybe like if you have this, then factor. Okay. So when you factor your numerator and your denominator, you should be able to cancel something out. So after you make the cancellation, then you'll try to plug in for x again. To try and get the answer for the limit, okay? Now, when we had x squared minus 9 and we factored it as x minus 3 times x plus 3, so some of you were pointing out that was a difference of squares, so it's maybe useful to know the difference of squares formula. So whenever you have a difference of squares, a squared minus b squared, you can always factor it as a minus b times a plus b. And if you wanted to confirm that, it's easiest to work backwards. So if you take a minus b and multiply it with a plus b, remember that for something like this, to multiply it, you kind of have to like FOIL the expression out. So FOILing will give us like a times a, which is a squared, plus a times b, minus b times a, minus b squared. And when you FOIL it out, you can see that the ab minus ba terms will cancel. So that's how it gives you a squared minus b squared in the end, okay? All right, so that was kind of the first slightly more complicated example of a limit. Maybe any questions so far about any that I've gone over? Yeah. So if factoring doesn't work, there are other techniques, and we'll go over some of the other ones over the next few days. Someone mentioned L'Hopital's rule earlier in the chat. And so L'Hopital's rule is a very powerful technique for dealing with indeterminate forms, although we're probably not going to cover it, I don't think. Maybe at the very end we might be able to cover it, but I wouldn't count on it necessarily. Now, does that mean that there is a hole at x equals 3? That's a good question. So here the answer would be yes. So if you were to graph this function, I don't know what the graph looks like. Might have been a good idea to actually have the graph available. But what would happen is at x equals 3, in the graph, there would be a hole. Okay. So it would, I don't know what it looks like, but it'd be something like this, maybe. I don't know, okay? But the function is not actually defined at x equals 3, because if you try to plug in 3 for x, you had the division by 0, so that makes it undefined. That's why you end up having a hole in the graph, okay? But we just calculated the limit was equal to 1/9. So that's how we would know that the hole had this y value of 1/9, so that the function was approaching the y value of 1/9 as x was approaching 3, okay? Any other questions? Yeah, okay. So I did say earlier on that I wanted to give you guys some time to practice on some problems yourselves. So here I've got another problem of a similar type. It's a polynomial over a polynomial. If you try to plug -2 in for x, you'll get -2 squared is +4. 7 times -2 is -14. And then in the bottom, -2 squared is +4. 9 times -2 is 18. So when you plug -2 in for x, you're going to get 0 over 0, so it's indeterminate. So I figured we can maybe pause for about maybe 2 minutes here. So you guys, if you have like some paper or whatever in front of you, try to work through this problem the way that we did in the previous example. And then after maybe 2 minutes or so, we'll go over the example. Okay. All right. So go ahead and try and practice and figure out what the value of this limit is. Okay, all right. Yeah, once you guys have an answer, feel free to post in the chat. And then, no harm in getting the problem wrong. Nothing wrong with that. Okay. So just kind of practice and then we'll go over it together. Okay, all right. That's pretty good. So the general consensus seems to be -1/5. So let's try and verify if that's the case or not, okay? So what we want to do is we want to try and factor this right now. And so, yeah, okay. In order to factor this, the numerator is a little bit more complicated, so maybe I'll do that one off to the side. So we've got 2x squared plus 7x plus 6. So if we wanted to try and factor this, there's like different methods of doing it. The way that I kind of learned how to do this myself was I first start by multiplying the 2 and the 6 together. So you multiply those two numbers. In this case, we get 12. So then what we want to do is we want to find two numbers that uh, that will multiply to be 12. But we also need them to add to 7. So the number in the middle. Okay. So then thinking about two numbers that will satisfy this condition. Those would be 3 and 4. So 3 times 4 is 12. 3 plus 4 is 7. Okay. So then once we find those two numbers, what we want to do is we want to rewrite this expression as 2x squared plus, and then we're going to take the 7x and we're going to write it as 3x plus 4x, or 4x plus 3x. It actually doesn't matter which way you do it. I'll write it as 4x plus 3x because that'll look nicer, but either way, you'll still be able to factor. Okay. Okay, so I took 7x and I rewrote it as 4x plus 3x, and then what we're going to do is we're going to factor by grouping. So in this first two terms, you can factor out a 2x, and that will leave us with x plus 2. And then in these two terms, you can factor out a 3, leaving us with x plus 2 again. Okay. But now we have x plus 2, which is common to both terms. So what that means is we can actually factor an x plus 2 out. And then when you factor out the x plus 2, you'll be left with a 2x in the first term, and then plus 3 remaining from the second term. So altogether, this will factor as 2x plus 3 times x plus 2. Okay, great. In the denominator, if you want to factor that, that one's a little bit easier. So we want two numbers that multiply to be 14 and add to be that would be 7 and 2. Okay. So once you factor, if you 0 over 0, then once you factor it, you should be able to cancel some terms out. And then after the cancellation, we're going to try plugging in -2 for x again. Plug in -2 for x, it's -4 plus 3 is -1. And then here you get -2 plus 7 is +5. So the answer should be -1/5, all right? So I think most of you were getting that, so that's pretty good. Yeah, okay. So factoring is a very important skill to have in calculus, at least in the courses here. So if you guys aren't familiar with how to factor polynomials, at least quadratics, you'll definitely want to practice that. Okay. There's different ways of doing it. I've seen people do all sorts of stuff when I've been tutoring them. I don't know all the different methods myself. Sometimes it kind of looks like magic what people are doing, but it seems to work because they get the right answer. So, however you guys learned it, just be sure that you are comfortable factoring your polynomials. And if you're not too familiar with it at the moment, it'll be good to maybe try to learn how to do it and maybe practice to become proficient in it. Okay. Okay. Now, there is a useful tip for factoring when you are dealing with limits. Okay. So one little tip that I can give is, so in this situation, we plugged -2 in for x, and we had 0 in the numerator and the denominator, right? So because -2 was one of the zeros of the two polynomials, that means that x plus 2 should have been one of the factors. For both the numerator and the denominator. Okay. And you can see that that is kind of what we discovered when we factored both of them. X plus 2 was a factor in each, okay? And so you can kind of use this idea to kind of help you out. So, if -2 was a 0, then x plus 2 should have been one of the factors. Uh, let's say if you had a problem like the first one, you can look at something similar going on here. So since the numerator and denominator were both 0 when x was equal to 3, that means that x minus 3 would have been a factor in each of them. And that's what we found when we just went through the problem, okay? So because you know one of the zeros, that's going to help you in factoring the numerator and the denominator. So say like if we knew that x plus 2 was already one of the factors, then we could have maybe figured out the other factor as being 2x plus 3 without going through this process, because you could have maybe just figured it out once you knew one of the factors. That said, you won't always be able to see a 0 of a polynomial when you're trying to factor it, so it is still good to know general techniques for how to factor as well, okay? All right, so any questions before I move on to the next example? All right. So here we've got another example. Looks a little bit more complicated now, perhaps, because we kind of had like fractions inside of a fraction. Let's just start by plugging in 1 for x. So if you plug in 1 for x, you're going to get 1 over 3 minus 1 over 3 over 1 minus 1. So that's another 0 over 0 situation. So we have this indeterminate form. So if you get 0 over 0, that means you have to try and do something to resolve it to get to the actual answer. So in a situation like this, there's not really anything to factor because we don't really have polynomials that we could try to factor here. But basically, you want to try and simplify this expression. And usually, to try and simplify something like this, you want to start by combining your fractions by getting a common denominator. Okay. So, for instance, when we look at the numerator, in order to combine the two fractions, 1 over x plus 2 minus 1 over 3, we're going to need a common denominator. So common denominator will be 3 times x plus 2. So what we're going to do is we're going to multiply the first fraction by 3 over 3. So that way we can get a 3 in the denominator. And then for the second fraction, we're going to multiply top and bottom by x plus 2 to get the x plus 2 in the denominator. And then that way we'll have common denominators and we'll be able to combine them in the next step. All right. Okay, so if we try to combine everything, we have a common denominator 3 times x plus 2. And then in the numerator, we're going to have 3 times 1 is 3 minus, and then we've got 1 times x plus 2. So we have minus x plus 2. Okay. And notice that I'm being careful there, and I'm putting parentheses around the x plus 2 because we were subtracting that whole quantity. All right, and then we still had, this was just everything numerator being combined. So then we still have the x minus 1 that was in the denominator as well. Okay. All right. So then we still have a fraction instead of a fraction, and so that's not very pleasant. So we want to simplify that as well. So the way that we can simplify this, there's 2 ways we can think of this. So instead of having everything divided by x minus 1, oh well. Dividing by x minus 1 is the same as multiplying by the reciprocal, 1 over x minus 1. If that's a little bit confusing, some people find it easier to think about it like this. So they'll say that x minus 1 is the same as x minus 1 over 1. So now it looks like you're dividing by a fraction. And so to resolve that, you multiply by the reciprocal. So multiplying by 1 over x minus 1, okay? All right. And then at this point, I think we are almost done, so just a little bit more work. So in the numerator, if we distribute the minus sign and simplify this, we'll get 3 minus x minus 2, because minus will distribute to both terms. So that'll leave us with 1 minus x. And then we still have 3 times x plus 2 times x minus 1 in the denominator. And at this point, we want to try and cancel something out again. So in order to try and cancel something, I guess what we'll want to do here is factor a negative sign out from the numerator. So if you factor out a negative sign from the 1 and the minus x, you'll be left with a positive x minus 1. And it's at this point where you can cancel the two x minus 1s now. Okay. And once we make that cancellation, we can then try to plug in x equals 1 to get the value of the limit. So if you plug in 1 for x, you're going to get 3 times 3 is 9. So it looks like the answer is going to be negative 1 over 9, okay? All right, so this problem was a little bit more complicated. So remember that when you're working with fractions, just remember some of those rules. So to add or subtract them, you need to get a common denominator. When you're dividing by a fraction, you multiply by the reciprocal. And still for this type of question, you should at some point be able to cancel something from the numerator and the denominator. And after you make that cancellation, that's where you can try plugging in for x again to try to get the answer, okay? All right, so any questions about that? All right, cool. So once again, I've got like another practice problem for you guys to work on. Okay. It's more complicated, but it's still the same type of question. You have like fractions inside of a bigger fraction, okay? If you try to plug in negative 1 for x, you should get another 0 over 0 situation. Okay. So let's take another like 2 or 3 minutes to have you guys try and work on this problem on your own. And then after you guys practice it a little, we'll go over it together again, okay? So as you guys are going through it, just kind of remember to try to combine the two fractions in the numerator. Try to combine the two fractions in the denominator. To do that, you'll need to get a common denominator for each of them. After that, you'll be dividing by a fraction, so you'll need to multiply by the reciprocal. And at some point, you should be able to try and cancel something out from the numerator and the denominator, okay? So do try and work it out. Don't be afraid to do so. And we'll go over it together. Okay. All right. Has anyone else gotten a different answer or maybe the same answer? Okay. All right. Let's go ahead and try to go through it together. I do believe -8/25 was the right answer. So let's try to verify that, okay? Okay, so the first thing we would want to do for this problem is combine the fractions in the numerator and the denominator. So in the numerator, we'd have to multiply the first fraction by 5/5 because we needed a 5 in the denominator. And for the second fraction, we need to multiply by 4 minus x over 4 minus x because we needed the 4 minus x in the denominator. We'll do similar in the like a big denominator. So 1/2 will be multiplied by x squared plus 1 over x squared plus 1. And then this next fraction, we're going to have to multiply this one by 2 over 2. Okay. So then simplifying the numerator, we're going to have a 5x plus 4 minus x. Okay. And in the denominator, we have a common denominator of 2 times x squared plus 1. And then we're going to have 1 times x squared plus 1 is just x squared plus 1. But we have a minus 1 times 2, so minus 2. Okay, so we'll simplify this a little bit. So 5x minus x is 4x. Okay. And then instead of dividing by a fraction, we want to multiply by its reciprocal instead. So we're going to multiply by 2 times x squared plus 1 over. And this x squared plus 1 minus 2 can simplify it as just x squared minus 1. Okay. All right, so then at this point, you'll want to try and factor a little bit because you want to try and cancel something from the numerator and the denominator. So in the numerator, you can factor out a 4 from the 4x plus 4. And in the denominator, the x squared minus 1, it's a difference of squares. So it'll factor as x minus 1 times x plus 1. Okay. Let me see, where is that? Oh yeah, 1 minus 2 gave us minus 1 in the end. Okay, so we just combined the 1 and the minus 2. Okay. So we kind of factored everything that we could, and once we factor, we see that we can cancel the x plus 1s. And then after making the cancellation, we'll plug -1 in for x to try and get the answer. So here we have 4 times 2 is 8. And if you plug in -1, squared becomes positive, so 1 plus 1, so get 2 for that. And then the bottom, 5 times, here you're going to have 4 minus a -1. It's like 4 plus 1. And then -1 minus 1 is -2. Okay. So I guess you can cancel the 2's out, and we are going to get -8 over 25 as the final answer. Okay. All right, so all right. I don't know if you guys have any questions about that. I'll pause briefly. All right, so no questions. I think that's good. So before I move on to the next problem, I just wanted to mention something. So if you notice the way that I am writing out my work, you'll notice that I carry the limit with me at each step of the problem until I get to this point here. So once I start plugging the -1 in for the x, that's where I drop the limit sign. So this is just kind of like a proper notation when you're writing out your solutions to limit problems. What your professors will want you to see is to carry the limit at each step, because at each step you are still like evaluating a limit. And at the point where you can drop the limit, that's when you plug the value in for x, because at that point you're saying the value of this limit should be equal to this number that you're getting. Okay. So just kind of keep in mind that notational practice of carrying the limit sign with you at each step. until you plug in the number for x. Okay. So I'll do one more example. I'm gonna stop doing that. Okay. All right, so now we have another example here, and again, there's something new to it. So what's new about this example is the presence of the square root. And if we were to try and plug in 4 for t, I guess I switched up the variable this time. It's not a big deal. If you try to plug in 4 for t, you're going to get 8 plus 1 is 9. Square root of 9 is 3. And then in the bottom, 4 squared is 16. So we do have a 0 over 0 indeterminate form. So therefore, we will need to do something to the problem in order to try and resolve that. And in the case where you have a square root in your problem like this, there's sort of a standard trick or a standard technique to apply. So for limits involving square roots, where you get 0 over 0, the standard trick is to multiply the numerator and the denominator by what we call the conjugate. So let me just explain what the conjugate is. We kind of saw it earlier actually, but the expressions a plus b and a minus b, these expressions are what we call conjugates. So a plus b is the conjugate of a minus b, and vice versa, a minus b is the conjugate of a plus b, okay? And we saw earlier with the difference of squares formula that when you multiply two conjugates together, it gives you a difference of squares. So this is useful whenever we have a square root in the problem, because after multiplying by a conjugate, since everything is squared, any square roots that you may have had will get canceled out by the square operation, okay? And so we'll kind of see how that works in this example. Okay, we'll see if that's the right answer. So what we're going to do is the following. In the numerator, with the square root expression, we think of the numerator as having the form a, where a is the square root and b would be 3. So the conjugate of a minus b would be a plus b. So we're going to multiply the numerator by square root of 2t plus 1 plus 3. And we can't do that just to the numerator. We have to do it to the denominator as well, so that we're not actually changing the question. Okay. So we're going to multiply top and bottom by the conjugate like that, and then In the numerator, since you're multiplying by conjugates, we know that the result is going to be a difference of squares. So it's going to be a squared minus b squared. Okay. In the denominator, you don't need to multiply it out, so just leave it as multiplying by the conjugate. You could FOIL it out, I suppose, but that's not going to make things better, so it's better to just leave it like this instead. So now we want to start simplifying this a bit. So as I kind of talked about earlier, the point of multiplying by the conjugate was to get rid of the square root here. So square root squared, those will cancel out. So we just get 2t plus 1, and then 3 squared is 9. And in all the problems that we've done, we've seen that we want to try and cancel something out from the numerator and the denominator. So I think what I'll also do at this point is t squared minus 16. I'm going to go ahead and factor that for right now. So t squared minus 16, again, it's a difference of squares. So you can factor it, in this case, t minus 4, t plus 4. All right. And just simplifying, 1 minus 9 is negative 8. And in the numerator, if we factor out a 2 from both terms, you'll get 2 and then times t minus 4. The t minus 4s are going to cancel now. So once you're able to make a cancellation like that, then try to plug in your numbers. So in this case, if we try to plug in 4 for t, we just had 2 remaining in the numerator. Here in the denominator, 4 plus 4 is 8. And then here we plug in 4 for t. We get 8 plus 1 is 9. Square root of 9 is 3. 3 plus 3 is 6. I guess you can maybe say 2 goes into 8 4 times. So you're going to get 1 over 24 for the answer then. Okay. All right, so this is just like another type of question that you can see, a limit involving a square root and 0 over 0 indeterminate form. If you have this kind of situation, usually you want to try and multiply the numerator and the denominator by the conjugate, because that will get rid of the square root and allow you to then try to maybe factor and cancel something out. Okay. All right. So there's not that much time left, so I'll maybe let you guys decide what you want to do. So do you guys want to work on another practice problem, or do you maybe want me to talk about the last topic that I had prepared, which is, I think, not super important, but still maybe something relevant that you guys might want to see. Okay, all right. let's go on to the last topic. Maybe just for anyone who wants to have some fun later. This is the practice problem I was going to have you guys work on. So it's a sort of a combination of the last two types of examples that we saw. So it involves square root and also fractions within a larger fraction. So if you guys want to give this one a shot on your own time, you are welcome to do so. I believe the answer, if I did all my work correctly, is 45 over 28. So if you guys want to try and practice it and see if you can get that answer, okay? So before I get to the last topic, I would like to go back to my slides real quick that I started with at the very beginning. So I left off at this point here where we were going to look at a certain math meme. All right. I'm guessing those are tears of joy at how beautiful that last example problem or practice problem was. Okay. So if you guys have seen any math memes before, then I think there's a good chance that you've seen this one, but we'll kind of go over it anyways, okay? Let's see here, let me flip my laptop. Whoops. Okay. All right. The math meme starts with this. We have a circle with a diameter equal to 1. Okay. So because the diameter is equal to 1, the area of this circle is equal to, what do I want the area? No, I guess I want the circumference instead. So the circumference of the circle will be equal to pi. Okay. So what we're going to do is we're going to draw a square around it. And because the diameter of the circle is 1, that means the overall perimeter of the circle is equal to 4 right now. Okay. Yeah, I'll include the slides in the video description of the in YouTube, and I'll try to link my OneNote to it as well, so you guys can also see the work that we did here as well. Okay. Okay. So we have the circle, and then we drew the square around it. So what we're going to do is we're going to remove these like 4 corners from the square. Okay. Now notice that the overall perimeter of this like outer polygon surrounding the circle, the perimeter is still equal to 4, because although we removed these lengths, we sort of regained them here and here, and we had the same thing in each of the 4 corners, okay? So we remove the corners of the square, but the perimeter is still equal to 4. And we can imagine doing a sort of infinite process again, where we remove more and more corners at each step. And as we keep removing more and more corners, the perimeter of the outer surrounding polygon is still going to be 4. So if we were to allow this process to continue to infinity, the limit would appear as if that the outer polygon sort of converges to the circle. But we know that the circumference of the circle was pi, And we also know that each step that surrounding polygon had a parameter 4. So if you repeat to infinity, the conclusion that one would sort of make is that therefore pi must be equal to 4. Okay. Yeah, and I'll show the problem again at the end. Okay. Okay, so I guess the sort of moral of this meme that we just saw is that the details matter. So you can't necessarily just like naively apply like limits and whatnot to a problem. So there are situations like this one where it seems like the result that you get, there's something wrong with the result that you get because the result that we're getting is pi is equal to 4, and we know that that's not true. Okay. So there's some kind of subtlety to what happened in this sort of infinite process. And if you like overlook that subtlety, then you'll reach a wrong conclusion like this. Okay. So the details matter. And so going back to limits, so far we've been talking about limits. We've even done a couple of examples of how to calculate limits, but we never actually talked about what does this statement that we're writing, this mathematical statement, what does this actually mean, okay? We'll post it later today to YouTube. So just check our YouTube channel. It'll definitely be up by tonight, I would say. It takes e-learning a little while to process the recording, so we won't be able to upload it right away, but definitely by tonight it should be uploaded though. All right, so then I guess to round out the review, I wanted to just talk about, what is the meaning of this mathematical statement that we have. So we've talked about it intuitively so far. So I guess the intuition would be that this statement means that, okay. So this statement is saying that the function f of x approaches the value of L as x approaches the number c. Okay. All right. So this is just sort of intuition though, but if we take a look at this English statement that I wrote out, I guess the word approaches is not very precise terminology. It's doing a lot of heavy lifting, if you will. So we want to, at these last couple of minutes, I want to try to like formulate a precise definition of limit at the very least. Don't think we'll have time to go over any examples, but I don't think that's that big of a loss though. It's not super important in your class. So, but I at least want to go over the precise definition because it is something that you will encounter and you will have like some problems on it at least. So in order to get a better sense for, how would we actually try to define a limit? I thought I would maybe consider like the following example. So let's consider the following sequence of numbers that I'm going to write out. So I have the numbers 5.1, 5.01, 5.001, and so forth. So just consider this sequence of numbers that we have. These are decimals. Okay. So if you look at this sequence of numbers, and if I were to ask you, what does this sequence of numbers approach? What would you guys say? What does this sequence of numbers approach? So I assume you guys said that it's approaching 5, right? Okay. Okay, so if I look at this example though, all of these numbers, they're all getting closer and closer to the number 5, but they're also all getting closer and closer to, say, the number 4.99, okay? So could we not say that this sequence of numbers is actually approaching 4.99 instead of saying that it is approaching 5? What do you guys maybe think of that? Would you say that this sequence of numbers is approaching 4.99, like instead of 5? Like, how is um, 5, I guess, different from the number 4.99 in this example? um, I've heard that mathematicians make good lawyers actually, because mathematicians are doesn't need to be very precise, I guess, with definitions, and that's maybe similar with the need for a lawyer to be very precise with readings of laws and things like that. So, okay, all right. So you guys are kind of noting some things that maybe distinguish the number 5 from the number 4.99. So one thing that someone said was that these numbers will never get past 5. So let me maybe try to draw like a picture. Let's say here's the number 5, and here's the number, I guess we'll say that was 4.99. Okay. So I think the observation that these numbers never get past 5, I think that's kind of a good observation. So in particular, if I look at this picture here, there's this sort of gap, this length for this distance of 0.01. And so although the numbers in our sequence they are getting closer and closer to 4.99, but there's this sort of gap, if you will, that they'll never be able to pass, okay? So the numbers of the sequence, something that we'll know is that the sequence is always at least a distance of 0.01 away from the number 4.99. Okay. Whereas in contrast, if we look at the number 5, there is no sort of gap between the number 5 and the sequence, in the sense that if we were to try to add a small distance to 5, so let's consider like if we did something like we added 5.00, and so if we added 0.00001 to 5, and we got that number there. So we have this tiny little gap between these two numbers. Okay. Well, if we look at the terms of the sequence, okay, I guess every number in the sequence after 5.00001, all of these terms will be within this tiny little gap that we had there, okay? And I could try to choose like a smaller and smaller distance from 5, but at some point, the terms of the sequence here, at some point, all those terms are going to be within that gap. So whereas for the number 4.99, there's the sort of distance that the sequence can never get closer to. But for the number 5, there is no distance that will separate 5 from all the terms within the sequence. Okay. So that idea kind of forms or informs us of what the precise definition of a limit should be. And so just to try to wrap things up, I've written out what the precise definition is over here. Okay. So the precise definition is phrased in terms of these Greek letters epsilon and delta. So people will usually refer to this as the epsilon-delta definition of a limit. But yeah, those symbols, they're Greek letters, epsilon and delta. So I think it took about, it took over a century for mathematicians to finally come up with this definition of a limit, like from the time that I guess calculus was invented to the time that they finally came up with this definition. I think it was over a century. And the way that they ended up phrasing it in the end is they said that this mathematical statement, that the limit as x approaches c of some function f of x is equal to L. What this means, it means that for every number epsilon greater than 0, there exists a number delta greater than 0, such that if x is within a distance delta of c, then f of x will be within a distance epsilon of L. And here I wrote this out in words, but you'll usually see this written out in terms of absolute value inequalities instead. So the absolute value of x minus c measures the distance between x and c. So if that distance is smaller than delta, then the distance between f of x and L will be smaller than epsilon. So they'll usually write it in terms of absolute value and inequalities like that. And basically what this definition is saying is, if we consider any distance epsilon from L, okay, we should be able to find some distance delta from C such that if x is within this distance delta of C, then f of x would be within a distance epsilon of L, okay? And because we allow for epsilon to be any number, essentially what we're saying is no matter how small of a gap we try to put in between, like around L, at some point, if x is close enough to C, the values of the function will be falling within that little gap. So there is, kind of like in this example here, all the terms of the sequence will approach 5. So no matter how small of a gap you try to put around 5, at some point the terms of the sequence will fall within that gap. It's the same thing here. So no matter how small of a distance epsilon you put around L, if x is close enough to C, then f of x will be within that distance of L. So that's kind of the idea of the epsilon delta definition. You don't do too much with it in your calculus sequence, but you'll do a little bit with it. So I thought it would be good to just kind of introduce it to you guys. Okay. So we'll go ahead and wrap up the review with that though. Tomorrow, my colleague Les will be going